Hello, everyone. My name is Noah Schwartz, and I look after engineering for AWS Data Exchange. And today we're going to talk about how to use data to optimize your daily fantasy sports football lineups. Before getting started, I want to share a little bit about what inspired me to do this session. Around 10 years ago, I co-founded Bloomberg Sports, and the idea was really simple. The Bloomberg terminal gives users access to the world's best financial data analytics, and we wanted to do the same thing for sports and really lean into the growing trend of using analytics to win. For example, evaluate athletic performance the same way you'd evaluate a stock, and use that evaluation to build the best team of players the same way you'd build the best portfolio of stocks. This was around the time of Moneyball, and analytics in sports was becoming more and more popular. And truthfully, I wasn't really into sports then, but I developed a passion for it as I learned more about the analytics. Eventually, I moved on to other jobs, but I remained passionate about sports and analytics specifically. And then daily fantasy sports started in 2012, and I became obsessed. The idea that I could write software that was smart enough to give me the optimal lineups for daily fantasy sports was something I couldn't stop thinking about. It just seemed so easy. Remove the emotions of picking players by scraping data, throw machine learning at the problem, generate the best lineups, and play daily fantasy sports professionally for the rest of my life. I tried for years, and I think obviously it didn't happen. As you can see, I'm sitting here talking to you about it. So for those of you thinking that this session will give you a reliable way to generate the best lineups week after week, I'm sorry, it won't. But I did have a lot of fun trying. I learned a lot, and I want to share that fun and learning with you today. Looking back on the models I built myself, the hardest part was getting good, clean data. Back then, AWS Data Exchange didn't exist, so it wasn't easy for someone like me to get data from a company like Stats Perform. So I had to scrape the data myself. That took a lot of time, and it was error-prone. But now, thanks to AWS Data Exchange and Stats Perform listing their data on our service, especially their free listings, the data is just a click away in my browser. So let's run through the agenda quickly. I'll talk about AWS Data Exchange itself and why we're so excited about it. I'll talk about daily fantasy sports, we'll talk about football, and we'll talk about why it's hard to find that optimal lineup. I'll suggest a smarter way to optimize your lineups using data from Stats Perform delivered through AWS Data Exchange. And then we'll look at the architecture of that smarter way to play, followed by a demo where we step through the code. So more than 90% of what we build at AWS is based on what our customers tell us they need, and we heard the same thing over and over again from data providers and data subscribers. Providers want a managed solution for data entitlements, billing, and secure distribution of their data at scale without having to provision new resources such as an S3 bucket or an SFTP for each customer. And subscribers have told us that they want the experience of finding and using data on the cloud, where more and more data is being stored and generated every day, to be as easy as it is to shop online. Many subscribers today actually need to reach out of the cloud to pull their data in, for example, from an FTP on a schedule, or maybe they even have to sideload a hard drive. And that's a weird experience when you're otherwise operating in the cloud, but for some reason the data isn't where you need it, close to your compute. What subscribers really want is to have the data pushed to them where they are in the cloud with as little setup as possible. So, in November 2019, we launched AWS Data Exchange, which makes it easy for customers to find, subscribe to, and use third-party data in the cloud. There's a lot of value here, so I'll highlight just some of it for you. As a subscriber, it's a single place to find all your third-party data. And you can automate delivery of that data to your S3 bucket via Amazon EventBridge. You can see and manage all of your subscriptions in a single place, and you can pay for all your third-party data using your AWS account. AWS Data Exchange also supports custom offers and private products. So data providers can issue bespoke products with custom pricing and custom terms as needed. And you can learn more about AWS Data Exchange at the end of the slide with the links provided. Today, AWS Data Exchange has a global public catalog with more than 2,700 data products from over 180 data providers. And all of this data can be accessed and used from a single console under a single API with automated ingestion into any AWS analytics, database, or machine learning service. And this presentation is a great example of that integration, as you'll see data from Stats Perform pulled into an S3 bucket and used in an Amazon SageMaker notebook to generate optimal lineups for daily fantasy sports. Okay, so let's talk about daily fantasy sports. In regular fantasy football, you draft a team of players at the beginning of the year, and that's pretty much your team for the year. You score points based on how well your players do in their game that week, and if you score more points than your opponent, you win. It's very simple. Daily fantasy sports is similar, except you pick a new team each week, and you and your opponent can actually pick the same players. But you can't simply pick the quote-unquote best players. Each player has a salary, and you need to stay under the salary cap. Still, this might sound easy, but it's actually really hard. Here's an example on the right from a daily fantasy sports game that I played recently. You can see I had to pick a quarterback, 2 running backs, 3 wide receivers, and so on. And I picked players based on gut instinct, and I did okay. I actually did better than 90% of players in this contest, but I was nowhere near the winner of the contest, who scored a whopping 253 points against my own 171. And the math on the number of combinations of players gets large very quickly. On a week where every team is playing in a format like the example here, you pick from 30 quarterbacks, then you need to pick 3 wide receivers from a pool of 80 or more players, then 2 running backs from a pool of 20 or more players, and then you still need to pick a tight end, a flex player, and a defense from a large pool of players. And it multiplies out to trillions of possible lineups in some cases. Picking the best lineup based on your instinct of who you think the best players are out of trillions of options is not going to work in your favor. And to make this even more complicated, in a lot of daily fantasy sports contests, you want to play multiple lineups. That way you get exposure to more players, and you're protected from a single player not scoring any points. So you really need the top 10, 50, or maybe even 100 lineups depending on how much you're playing. So you need a data-driven way to optimize these lineups without having to evaluate trillions of combinations. So I already talked about there being so many combinations and it's hard to pick the best lineups. But if you forget daily fantasy sports for a minute and just look at football, it's hard to even predict which team is going to win. You might think a specific team is a lock to win because they're just better than their opponent. But on any given Sunday, any team has a chance to win. And forget teams for a minute. It's even harder to predict what an actual player will do, which is what you need to generate optimal lineups. Coaches don't share game plans. And even if they did for some reason, those plans change throughout the game. Weather changes. What might have projected as a pass-heavy game becomes a run-heavy game if it rains or snows. And that means that different players will get more chances to touch the ball than you thought. And of course, players get hurt, which limits your ability to score points. There's a continuing theme here that football is unpredictable, making it hard to generate the best lineups for daily fantasy sports. So I've spent all of this time trying to convince you that it's hard to pick the right players, so we need a smarter way to generate our lineups. You can improve your lineups if you choose players based on data-driven decisions. So to start things out, we're going to leverage data from Stats Perform, the world's leading provider of sports intelligence data. Using historical box score data from Stats Perform, we're going to look at how players have performed historically in each of their games looking back the last 5 years. And for each of those games, we have the historical odds also from Stats Perform. So we know how players performed, and from the odds, we know the total score of the game predicted by odds makers, along with which team would win, by how much, and if it would be a close game. With this information, we're going to train models to tell us if a given player at a given position has a chance to score a lot of points based on the odds for their game, because points are what we need to generate the best lineups. And by predicting which players have a good chance to score a lot of points based on the odds for the game, we can shrink that player universe I talked about earlier, so that instead of looking at trillions of different lineups, we can look at just a few 100,000. And finally, with a smaller universe of players, we'll use player predictions and salary data from Stats Perform to generate the best lineups, increasing our chances of producing an optimal lineup without needing the compute resources for trillions of options. I know it's a lot of information, but don't worry, we'll go through all of this. On the next few slides in particular, we'll focus on what odds are, why they matter, and then you'll see it all come together when we step through the code in our demo. So odds look complicated, but they're actually very similar. So let's dissect this example. OU 57.5 minus 4.5 gorillas at neutrons. What does this mean? This is a game between the gorillas and the neutrons, and it's being played at the Neutron Stadium. OU stands for over-under, and it means that odds makers think the total score of the game will be around 57 points. The minus 4.5 is called the spread, and it means that odds makers think that the neutrons are going to win by around 4 points. This is meaningful because historically the most common total score of a football game is 41 points. So odds makers think that this will be a high-scoring game. And with a spread of minus 4.5, means that the neutrons are predicted to win, but they're predicted to win by less than a touchdown. So it'll be a close competitive game. You might be asking why the odds matter when picking individual players, because the odds are really about predicting the outcome for a team, and we care about players here. The reason is that the odds tell you a lot about how the game might be played. For example, a high total score with a large spread implies that the underdog will be playing from behind, but they will score points. So their quarterback might take a lot of risks to score those points, and that could be a good option in daily fantasy sports. A large spread could also mean that the winning team will run the ball a lot with their running back. When a team is winning, they tend to use up time in the game clock, and the best way to use up time in the game clock is with a running play. A small spread in a high-scoring game is really straightforward. It'll be a high-scoring, competitive game, which means it's a good way for you to score points. And going back to that example I showed earlier, it was based on a high-scoring game with a small spread. And using standard fantasy scoring, the quarterbacks in that game scored 29 and 36 points, which is well above the 20 or so you'd really hope to get from a quarterback playing fantasy football. So I'll show you a real example of why the odds matter for individual players by looking at the data. What you see at the top here are the average pass attempts by quarterback when their team is favored to win, grouped over the over-under in the stats perform data set. And on the bottom, you see the average passing attempts by quarterback when the team is predicted to lose over the same range. And I know a lot of this chart looks pretty similar, but when you look at the right end, you can see a little bit of a trend. In games where the team is predicted to win, their quarterback throws an average of 4 fewer passes when the over-under is over 57. This is a single example of what we want to capture in our machine learning models by looking at the odds. And now that we understand the odds, I want to spend just a few minutes talking about the architecture, and then we'll jump into the code. The first step is that Stats Perform publishes their data to AWS Data Exchange, which, as a reminder, includes historical player data, odds data, salary data, and player predictions. Then we spin up an Amazon SageMaker Jupyter Notebook to drive our models and lineup optimization. Then we pull stats from AWS Data Exchange into an S3 bucket so it can be used by our Amazon SageMaker models. After that, we train our machine learning models to tell us which odds are favorable for each position. Finally, after training our models, we generate optimal lineups using a linear optimization so that we can quickly compare the full universe against the universe of players with upside from the odds. As I mentioned earlier, when playing daily fantasy sports, you typically want more than one lineup so that you can get exposure to more players and limit the downside of a player not scoring any points. So if that smaller player universe is as good as the full player universe, it'll be easier for you to compute all possible lineups using a brute force algorithm so you can pick as many lineups as you need. And now it's demo time. To start things off, I want to show you how to get a subscription to the Stats Perform data in AWS Data Exchange. Starting from the catalog in the AWS Data Exchange console, I'll search for Stats Perform and select the Fantasy Player Data product. I already have a subscription to this product, but for those of you that don't, all you need to do is click Continue to Subscribe and wait for Stats Perform to approve this subscription. I'll click into my subscription, and you'll see that I have access to predictions data, salary data, odds data, box score data, and player and team reference data, all from Stats Perform. I can click into any of these data sets and export the data to an S3 bucket, but we'll be doing that in the Amazon SageMaker Notebook itself using the AWS Data Exchange APIs, so you'll see that in a moment. Before jumping into the notebook, I want to call out that this demo depends on familiarity with Pandas data frames, basic experience with Amazon SageMaker, and linear optimizations. And if I go through things too quickly in the demo, the code is there for you in the AWS Samples GitHub repository, so you can check it out, play with the code yourself, and learn from the links provided in the notebook. And with that out of the way, we'll move to the Jupyter Notebook. So I split the notebook into 7 steps, which I'll go through with you one by one so you know what's coming. In step 1, we'll get the Stats Perform data from AWS Data Exchange into an S3 bucket. In step 2, we'll join and massage that data so that it can be used to train our models. In step 3, we'll set up the parameters for our machine learning models, and we'll set aside data from the 2019 season so that we can verify our models against it later on. In step 4, we'll actually train our models against data from the 2015 to 2018 seasons. And then in step 5, we'll get the data ready from the 2019 season so we can see how the models perform in practice by generating actual lineups. In step 6, we'll take a slight detour and look at how much smaller the player universe is now that we're looking at players with upside from the odds, as I discussed in the slides. And then finally, in step 7, we'll run a linear optimization to look at the best overall lineup from the full player universe, and we'll compare that to the universe of players with upside in the 2019 season to see how our models actually perform. So in order to run the code in this notebook in your own AWS account, there is some setup required, which I've detailed here for you. In short, you need an S3 bucket, an IAM role with permissions that I've outlined for you, and a subscription to the stats perform data product that I just showed you. I'll note here that I've pre-run all of the code in this notebook, so we won't be running it live. But if you follow the setup instructions, it should just work in your own AWS account. And the reason I won't be running the code live is that it takes an hour or so to train the models, and I only have 30 minutes with you. And with that done, we can start getting into the guts of the notebook in step 1. As our first step, we need to export the stats perform data from AWS Data Exchange into an S3 bucket. We do this so we can point Amazon SageMaker at the data to train our models. This step is really as simple as creating an AWS Data Exchange client using Boto3 and calling the APIs to get the files contained in the stats perform datasets. And once we have a list of files, we call the AWS Data Exchange APIs to export the data to our S3 bucket. And as you can see here at the end of step 1, I have the stats perform data exported to my S3 bucket. In step 2, we put the data together so that it can be trained on by our machine learning models. A lot of this is boilerplate, but there is one bit that I want to call out. In cells 21 and 22, we have a function that turns the odds. Remember, that's the over-under and the spread into what's called an implied score. Given that we know from odds makers the predicted total score of the game from the over-under and how far apart the winning team will be from the losing team from the spread, we're able to calculate the implied scores for each team. These values are important because, as you'll see later on, they're features for our machine learning models. What that means is that when we ask the machine learning models if a player has upside from the odds for their game, part of that decision will be made based on the implied scores of the game for each team. We could also just represent the data to the models as plain over, under, and spread, but then you would need another feature to capture whether the player is on a team that's predicted to win or lose. And it's possible that such a model performs better, and I encourage you to do your own experiments. But here, we'll be using implied game scores. So here, just before cell 25, I listed all the columns we'll need in order to train our model. I won't go through each of them, but there are a few that I want to call out. At the bottom, you can see we have the implied scores. As I said, these are features that machine learning models will use to determine if a player has upside from the odds. But we're also going to include how often the player had a chance to touch the ball. So for a quarterback, we'll also use passing and rushing attempts as features for our model. For running backs, we'll also use rushing attempts and targets by the quarterback as features in the model. And finally, for wide receivers and tight ends, we'll also be looking at targets from the quarterback in our model. And of course, the features on their own aren't enough. We need to know whether or not the player did well in their game. And so we calculate how many points they scored using a standard fantasy football scoring function. Later in this notebook, we'll use these points scored to label whether or not the player has have upside from the odds for their game. And finally, we have the data we need to train our model, and you can see a sample of 10 rows here. The critical bits, as I called out before, are the attempts, targets, implied score, and actual points scored, which you can see here to the right of the table. So, in step 3, now that we have our data, we can get ready to train our models. You may be wondering what I mean by models. Aren't we training a single model? What we're actually doing here is training one model per position, because what we really want is to classify whether or not a player has upside from the odds. And to make that classification easier for the models to learn, we have one model per position. Again, this is another area where I encourage you to do your own experiments. You can see here in cell 29 that I have an object that describes which features we use per position in our models. We also have qualifiers. We use these qualifiers to filter out players that didn't get enough chances to touch the ball in their game because their points scored will be close to 0, and that's going to skew our results. So for example, we only consider quarterback data points if they threw the ball more than 10 times in the game that they played. And with a qualified set of data, we also calculate what I'm calling the start quantile. Simply put, we take our players by position, sort them by points scored, and if they're above the start quantile, we label them as having upside. Having upside is the label we pass to our models we train, and it signifies whether or not the player should be considered to have upside based on the features input into the model. So for example, we say a quarterback has upside if they scored better than 50% of other quarterbacks over the 5 years of history that we're looking at. And at the end of step 3, after applying qualifiers and looking at the start quantile, our model will be trying to recommend quarterbacks that will score more than 17.3 points, wide receivers that will score more than 9.8 points, running backs that will score more than 10.8 points, and tight ends that will score more than 9.6 points. And finally, before moving on to step 4, I'll call out that we're setting aside all of the data from the 2019 season so that we can verify our model against it later on. So we train on data from the 2015 to 2018 seasons, and then to see how good the models are, we verify them against data from the 2019 season, which we set aside here. Step 4 is where we finally train our models, and we're about halfway through the notebook at this point. There's a lot more boilerplate here where we call Amazon SageMaker APIs, but what's really important is the model we're using. We're using a linear learner, which is good for classification problems. And as I said before, what we have here is a classification problem. We want to know if a player is classified as having upside based on the odds for their game. I want to call out that if there's anywhere in this notebook that I would start to further improve the model, it's here. There are a lot of hyperparameters, for example, the learning rate, that you can tweak to change model performance. I've included links at the bottom. And before we get to see if these models are any good, we first need to understand how to measure good. We can obviously measure the overall accuracy of the models by dividing the correct predictions by the total number of predictions made, but that measure can easily become meaningless. For example, if we have 100 players where 2 have upside and 98 don't, and the model says no upside for all players, then it's 98% accurate, but it also means that it can't identify players with upside, and that's what we want. So we introduced 3 machine learning concepts here to measure the quality of our models: precision, recall, and the F1 score. Precision tells us the percentage of positive predictions that were correct by dividing true positives by the total of true and false positives. Simply put, this tells you how precise the model is when it predicts a player has upside. Recall tells us the percentage of positive predictions that were recalled by dividing true positives by the total of true positives and false negatives. In a perfect model, all of your false negatives would be true positives, so this measures how good the model is at recalling which players have upside. So a model is more precise with fewer false positives and has better recall with fewer false negatives. And finally, to combine these two, we have the F1 score, otherwise known as the harmonic mean. There's an inherent tension between precision and recall, given that one is a function of false negatives and the other is a function of false positives. So the F1 score is a way to look at them together. So I talked before about seeing if these models are any good, and the truth is that it's hard to tell without having a solid baseline to compare against, which we don't have. But what you do know is that you need high precision and you need high recall. You don't want the model making a mistake when it says a player has upside, and you don't want the model missing out on recalling players that do have upside. You may recall in the previous step, we set aside 2019 data for verification. Well, in the previous cell, we ran the verification data against our models, and these are the results. Intuitively, these seem good, but you'd really want to see these measures for predicting higher point totals than the 10 or so we're looking for at wide receiver, running back, and tight end. In my own experience putting this notebook together, I saw that precision and recall get worse as you look for higher target point totals, which makes sense. The higher the points we want, the harder they are to find. And that would be a good way for you to reason about how to improve the models in this notebook. I'll go through this step very quickly because it's very similar to step 2. In this step, we get data from the 2019 season together along with salary and predictions data from Stats Perform. The salary data tells us how much a player costs so we can stay under the salary cap. The predictions data tells us how many points Stats Perform thought the player would score in their game. And of course, as these games were played in 2019, in the past, we know the outcomes. So we know how many points players actually scored, and we use this as a point of comparison later on for our models. I want to bring your attention to cell 48 because this is where we actually call our models on the 2019 data to label whether or not the players have upside. In machine learning terms, we call this inference. This will be critical in a moment when we actually optimize lineups. And here at the end of step 5, we can see a table with our players, their predicted points, their actual points, their salary, and whether or not the player has upside according to our models. So step 6 is a little bit of a pause that I've put in to help us appreciate how much smaller the player universe is when we only look at players with upside. This is a log scale chart for each week of the 2019 season. The blue line in this chart tells you how many lineup combinations there are if you look at the full player universe. And the green line tells you how many lineup combinations there are if you look at the upside player universe. And in week 1, I've noted that if you look at the full universe, there are over 420 trillion combinations, whereas with the upside universe, there are only 786,000. In many daily fantasy sports contests, you want to play multiple lineups, again, so you get exposure to more players and limit the downside of a player not scoring points. But you can't realistically calculate how well 420 trillion combinations will perform to find the top-end lineups you want to play. But with just several hundred thousand, you can. And finally, we're optimizing lineups. Here, I'll actually be using a linear optimization to find the overall best lineup so that we can see how the universe of all players compares against the universe of players with upside. As I just mentioned, you may want more than just one lineup for a daily fantasy sports contest. So if the universe of players with upside is able to compete with the full universe, then you can run a brute force algorithm to give you those top-end lineups on that smaller player universe. And I have left extensive comments in the code on how the linear optimization works, so I'll skip ahead to the plot of results so we can see how the models actually perform in generating lineups. The green line on this chart is the best lineup using actual points scored for each week of the 2019 season. The orange line is the best lineup using the entire universe of players for each week of the 2019 season from predicted data. And the blue line is the best lineup using the upside universe of players for each week of the 2019 season. The dotted gray line is the score total we're estimating you need to rank in a daily fantasy sports contest. On average, that's about 157, but you may have noticed that we didn't build a model for defenses. So we're subtracting 15 from that average and setting the rank line at 142. And as you can see, there are many weeks where the upside player universe outperforms or matches the full player universe. So even though you're working with a smaller set of players, you're still able to generate strong lineups. Still, the average score for the full universe is 164.4, which is 4.4 points higher than the 160 we see from the upside universe. So there's room for improvement here, which I leave to you. And before we wrap, I want to highlight just a few examples that might be worth a closer look to see where you can further improve the model, circled in red. In week 10, we have an example of the upside universe performing better than the full universe. It's worth looking at the poor performing players the upside model filtered out that week to see if there's a general pattern worth applying to all weeks. And as another example, in week 15, the upside universe performed worse than the full universe. It's worth looking at the high-performing players the upside model missed that week to see if there's a way to improve the model for all weeks. And as I've said, with a smaller universe, you can generate more lineups to get exposure to more players in your daily fantasy sports contests. Now, there's a lot of room for improvement here, and that's where the fun comes in. Earlier, I mentioned playing with the model hyperparameters, but in order for these models to be useful, you first need a model for defenses. Fortunately, the stats perform data includes what you need to calculate this. So if you're excited by what you've seen here, the data is there for you to make it a complete product. I hope you had as much fun watching this as I did building this. You can learn more about AWS Data Exchange and Amazon SageMaker by following these links. And you can see the free listings from Stats Perform on AWS Data Exchange as well as the code I ran here today in the AWS Samples GitHub repository. I encourage you to do your own experiments. The code and the data are there for you. Thanks for watching, and don't forget to check out these other great sessions to learn more about AWS Marketplace and AWS Data Exchange.